A picture is worth 1,000 words. In this module, we return to analysis phase, but this time, instead of looking at documentation, we're looking at diagrams or pictures. Sometimes diagrams are the best way to convey or communicate information about what our system is supposed to do. In this video specifically, we'll start with a type of diagram called a data flow diagram. And after this video, you'll be able to describe the purpose of a data flow diagram as well as list the components of these diagrams. Finally, we'll compare these diagrams to use case diagrams, which we looked at earlier. But first, let's take a look at where we are. This is the systems development lifecycle that we presented at the beginning of the course. As I mentioned, as a systems analyst, we're going to do most of our work in the analyze phase. We're still going to be in an analysis phase or analyze phase as we look at the different types of diagrams that we might draw to help describe what our system might do. In future modules, we'll take a look at the design and implementation phase. Specifically, in this module, we'll be looking at the different types of diagrams that you can draw in order to communicate the requirements of the system. We've already looked at documentation that we produced during the plan phase, and we've also looked at the kinds of documentation we produce in analysis phase. Specifically, we focused on requirements, test cases, and use cases. And in this module, we'll focus on two major types of diagrams that you might draw during the analysis phase. These are process models, which we usually use a data flow diagram for, and then data models, which we use something called an entity relationship diagram for. But we're going to start with data flow diagrams and the various components of them. You might remember something like this from the beginning of the course. This is called a context diagram. Now actually, a context diagram is really just a special subset of data flow diagram. You can think of it as the top level data flow diagram. It shows the relationship of a system to its external entities. In this case, we have a textbook example of a TuneSource digital music download system. You can think of this like Apple's iTunes, basically an online music store. The context diagram that you see here shows the relationship of the system to external entities such as customers, payment clearinghouses, and marketing managers. Of course, in a real-life scenario, this would be much more complicated. We've simplified it here for the purposes of discussion. There are three major components in a data flow diagram. We start with a process. Processes in a data flow diagram typically appear in a box with rounded corners. They have a name, and we'll talk about how to pick a name for each process as we move ahead. And then we typically give them a number. In the context diagram, you'll see here that we represent the system itself as one big process, and we usually, by convention, give it the number 0. I'll show you how the numbering scheme works in future videos. Also in a data flow diagram, we have these boxes. These boxes represent what are called external entities. These are people or other systems that might want to interact with this system in some way. Finally, we have the arrows that represent the flow of data between external entities and processes, or in between processes themselves. We'll talk about a lot of rules for how you draw these arrows, and you'll see that this diagram really has a very specific syntax to it so that it can be properly understood by a wide range of people. There are multiple different types of notation out there for data flow diagrams. Most of the examples that you'll see in this course use something called Gain and Sarson notation. There's also another notation out there called DeMarco-Jordan. Both of these notations are used equally, and you'll see a few examples of DeMarco-Jordan, but most of what we do will use the Gain and Sarson symbols. You can see here the Gain and Sarson symbols represent processes with a box with rounded corners. Both types of notations use an arrow to represent a data flow. We'll also talk about data stores, which can be anything from a computerized database down to a filing cabinet or even just a stack of papers on your desk. And you can see there's slight differences in how data stores are represented, and external entities are represented in both notations as a box. As I mentioned, in a future video, we'll talk about specific rules as to how you connect these items in your diagram. Finally, let's talk about the relationship of the data flow diagram to the use case diagram, which we looked at in previous lessons. There is a relationship, although it's not necessarily as strong as we would like. There are some things that are usually identical between the two. So for example, external entities in our data flow diagrams generally match up with the actors from our use case diagrams. Also, the title, which is essentially the name of the system, can be shared. However, data flow diagrams represent the flow of data, whereas use case diagrams are really representing a relationship between actors and use cases. And so in a use case diagram, you won't necessarily have labeled flows of data. The process names in our data flow diagram are usually similar to the use case names from our use case diagrams. However, there's often a minor difference because in our use case diagram, we focus on the user's perspective, while in the data flow diagram, we might focus on the organization or the corporate perspective. We'll dig into the various details of data flow diagrams in future lessons. One last note, in data flow diagrams, we typically represent additional detail by providing additional data flow diagrams. So for example, we start with a context diagram that you see here that has the primary system with the number 0. And in a future video, we'll show you how to decompose this into additional diagrams that provide additional detail. On the other hand, if you take a use case diagram, as we learned earlier, the detail for use case diagrams is often in detailed use cases, which include steps, preconditions, postconditions, and all of the components and elements we talked about in that lesson. From this point, we're going to take a look at data flow diagrams. We'll go into additional detail into how you put these diagrams together and the rules to make sure that your diagram communicates something effective to system engineers. The primary purpose of everything we do in analysis phase is communication. And just like the English language has grammar, there is a special syntax for preparing our data flow diagrams so that other people can understand them in an unambiguous manner. In this video, we'll start to dig into this syntax a little bit so you can prepare data flow diagrams that make sense to system designers. After this video, you'll be able to describe the purpose of higher level data flow diagrams, as well as evaluate whether a data flow diagram is balanced. Finally, we'll teach you how to decompose a data flow or a system into processes. Let's start by taking a look at how we provide additional detail in our data flow diagrams. On the left, what you see here is a context diagram, as we introduced in a previous video. This context diagram can then be decomposed into what's called a level 0 data flow diagram. The context diagram shows the overall system with its relationship to the external entities. The level 0 data flow diagram shows the major processes that make up this system. And as I mentioned, there are specific rules for coming up with these processes, as well as specific rules for drawing all of the lines that you see here. Let's take a look at those. We start, perhaps the easiest step, which is to take the external entities from our context diagram and effectively replicate them on our level 0 data flow diagram. That part is fairly easy. Next, we take the system from our context diagram and we decompose that into a set of constituent processes. These are called the level 0 processes. They're essentially the highest level processes that you can think of in the system. So here in our example, we have the TuneSource digital music download system. We decompose that into 3 level 0 processes: search and browse our tunes, purchase tunes, and promote our tunes, which might be done by our marketing managers. Now again, this is an overly simplistic example, but it gives you the idea. How do we figure out what our level 0 processes should be? Well, ideally, we've already prepared some use cases, and we have a use case diagram. So let's go to that. We can see that the level 0 processes in our DFD roughly correspond to the use cases from our use case diagram. Now, this isn't a hard and fast rule, but if you don't know where to start, this is a good place to start. You go to the use case diagram, pull the use cases, make those your level 0 processes, and at least it gives you a starting point. Finally, in our diagram, we want to make sure that we're in our level 0 diagram. We include new and additional information. In particular, we include these data stores. You see them here labeled with things like D1, D2, and so on. Each of this is a place where we store some data. We'll talk in a bit about the difference between physical and logical data flow diagrams, but for the purposes of this step, it's important that the data stores represent the what and not necessarily the how. So these data stores might end up being databases on a computer, or they might be, like I said, files in a filing cabinet, or as simple as a stack of papers on your desk. But we add in the data stores do not appear in the context diagram. However, they do appear here on the level 0 data flow diagram. One last concept, and this is perhaps the most difficult concept to understand, but the most important when it comes to making sure that your DFDs actually add clarity to the system, is that the different levels of data flow diagram need to be balanced. What we've done here is we've decomposed the level 0 DFD into a level 1 DFD. So we've taken our search and browse tunes process and we've decomposed that further still into something called a level 1 DFD that you see on the right of your screen. In the level 1 DFD, we've labeled our processes with numbers like 1.1, 1.2, and so on to show that these are effectively decompositions of the process on the higher level diagrams. It's important that these be balanced, and what we mean by that is that every data flow in or out of this process on the level 0 DFD needs to be accounted for on the level 1 DFD, and so on down the line. So in this case, we've got the relevant data stores, and notice we only include data stores that interact with process 1 on the level 0 DFD. And then from there, we check to make sure that all of the various arrows that go into or out of the process are accounted for in the level 1 DFD. I encourage you to take a minute, study the diagram, and try to convince yourself whether or not this is the case. You might be curious about the web promotions data flow that you see in the upper right. We can see in the level 0 DFD on the left that web promotions goes in, as well as time to buy comes out on the bottom. It might be hard to find these in the level 1 DFD on the right, but you can see that they're both accounted for, and they're both coming from or going to their proper respective data stores. Balancing, while it might seem like a tedious task, helps ensure that there are no inconsistencies in our data flow diagram that might lead to confusion when we get to time to implement our system. Just like a written or spoken language, data flow diagrams have their own syntax. And just like a written or spoken language, we can make mistakes that lead to errors of clarity, or essentially or ambiguity in what we're trying to communicate. In this lesson, we'll take a look at some of the rules for drawing data flow diagrams to make them as clear as possible. And we'll also take a look at the different types of data flow diagrams. If you've seen a data flow diagram before, you might be looking at some of the examples that are on the screen thinking, hey Ken, that's not a data flow diagram, because something you've seen is different than what you've seen before. Well, that's because there are different types of data flow diagrams, and we'll look at the different types. After this video, you'll be able to identify errors in a data flow diagram as well as name the notation used to draw a particular diagram. Finally, you'll be able to list and describe the different types of data flow diagrams and where they might be useful. Let's start by taking a look at some of the rules for our data flow diagrams. We see that every process has a unique name that is an action-oriented verb phrase, so it usually starts with a verb. Also, every process has to have at least one input and at least one output. If a process does not have any data flowing into it, then it's something we might call a miracle, because it creates information. On the other hand, if a process only has data flowing into it with no data flowing out, then we call that process a black hole for reasons that should be obvious. I'm going to put on the screen a sample data flow diagram. I'm going to ask you to take a minute while the video pauses and look at the data flow diagram, see if you can identify a black hole, a miracle, and also study the diagram carefully for anything else that might look suspicious. Let's take a look at where these examples occur in this particular diagram. If we look carefully here at process 312, create a new bank account, you can see that there are 3 data flows coming in, but no data flows going out. This is our black hole. If we look just below that, down here at process 313, you can see freeze member account number has information coming out of it, but no information coming in. This is something that we would call a miracle. And then if we look far on the right of the diagram, over at process 311, it says generate an employee bank statement. Well, this isn't necessarily a miracle or a black hole because it has data flowing in and data flowing out. It does look suspicious because can we really generate an employee bank statement with only the address as input? This is what I would call a semantic error. And in other words, it's an error in the meaning of the diagram, and it might lead to a lack of clarity down the road. Identifying syntax errors like black holes and miracles is often easy because you don't need any kind of familiarity with the domain of the system. On the other hand, identifying semantic errors like this one is much harder and usually requires reviewing the diagram with your business subject matter expert. I remember when I started my career, I worked for a company named Cargill in their grain division, and my background is computer science, so I knew very little about grain trading. I had to rely on the grain traders to tell me whether or not something made sense. And this is the kind of thing you want to run by your customer to see if it makes sense. Let's take a look at a few more guidelines and rules for our data flow diagrams. Again, the goal of all of these is not to be legalistic, but it's for clarity purposes. Every process should have, or every data flow has a unique name that is a noun and a description that goes along with it. And a data flow should connect to at least one process. That basically means that we shouldn't have any data flowing between our external entities in the diagram, and we shouldn't have any data flowing between data stores. All data should flow into or out of a particular process. And then data flows only in one direction, and this means that you shouldn't have any two-headed arrows. If we do have a situation where data flows from one process to another in both directions, then we should have two arrows on the diagram, one going one way, one going the other way, and properly labeled. The rest of what you see on the screen here are all good ideas to help improve the clarity of your diagrams, but in most cases you'll find that in real-world situations you often need to violate them in order to most closely approximate the process that you're modeling. This is a data flow diagram, and it probably looks different than what we've been showing so far. What you're seeing here is a data flow diagram in a different notation. This is what's called DeMarco-Jordan notation. If you remember, when we introduced data flow diagrams, we talked about two major different types of notation. And I'm just giving you this as an example of the other notation. You might come across this in industry, and I wanted you to be exposed to it so that you'd be able to identify what it is. For the most part, the meaning and the semantics is the same. The shapes are just slightly different. Let's finish up by talking about four different types of data flow diagrams. As I mentioned, if you've seen a data flow diagram before taking this course or watching this video, it might have looked different than what we're showing on the screen. That's because we use different types of data flow diagrams for different situations. Sometimes we use a data flow diagram to document our as-is process. In fact, most analysis starts by understanding how things are currently done. You'd be surprised at how little understanding there is sometimes of the current process, and sometimes even the process of analyzing the current procedures will lead to new insights. And so we often start by drawing a data flow diagram that represents the current process. This is an example here of a simple inventory system that has interactions with the supplier, inventory reports, and stock on hand. We can also draw data flow diagrams to represent what we call our to-be process. So, for example, we might draw the data flow diagram like you see on the screen that represents the process as we wish it to be. So we have an as-is data flow diagram as well as a to-be data flow diagram. After that, we get into logical and physical data flow diagrams. I often start by making a logical data flow diagram. This focuses on the what, but not the how. A physical data flow diagram, on the other hand, adds in detail as to how particular tasks are performed or how data is stored. So what you see here is an example of a physical and a logical data flow diagram approximating the same process. What you have on the right side of the screen is a logical data flow diagram. You'll notice that it does not make any reference to specific physical implementations of some of the processes in the data stores. On the other hand, on the left-hand side of your screen, on the upper left, what you see here is a physical data flow diagram. This diagram often has specific names, as you can see here, as well as specific locations where we might store particular information. The best approach is usually to start by drawing a physical, as-is data flow diagram. This is nice and concrete. So you talk about who does the current process, where things are currently stored, and so on. You then take that through a process of refinement to get to a logical DFD that represents the current process. You can then transform that logical DFD into a logical DFD that represents the 2B process. And then in your final step, you can take the logical 2B DFD and translate it into a physical 2B DFD that describes the new system as you wish it would be. Analysis paralysis is a term we often use when we analyze things to death without really making progress in our implementation. It can be the same when you're decomposing your data flow diagrams. How do you effectively know when to stop decomposing? In this video, we'll talk a little bit about what happens at the end of the DFD decomposition process when you've essentially decomposed the processes as far as they can go. After this video, you'll be able to describe why we decompose DFDs, as well as evaluate whether a DFD is decomposed to the proper level. Finally, we'll talk about the concept of primitives, and you'll be able to read and interpret primitives that are written in structured English or shown as a decision table. But first, in an earlier video, we talked about how we take our context diagram and decompose that into a level 0 DFD. We also saw an example of taking a level 0 DFD and making it a level 1 DFD. You can imagine that this process can continue almost indefinitely, decomposing your processes further and further. So how do you know when to stop? Well, one guideline is that the ideal level of decomposition is to decompose until you can provide a detailed description of the process in no more than one page. This usually means writing logic in something called structured English, or a decision tree or decision table. Let's take a look at some of these and what they look like so that you get an idea of what the goal is. For example, let's take this process, generate orders. We might decide that this generate orders process is decomposed further enough if we can describe it with one page of structured English. And here's what structured English might look like. We could use simple if-then language. So if an inventory level is less than the minimum order quantity, then we create a new order. Otherwise, we do nothing. If that's an accurate description of the process, then we don't need to decompose any further. Instead, our primitives are typically attached toward the end of our data flow diagram so that you can get descriptions of all these processes. Structured English is not necessarily intended to be a computer language, but you can see with logic like this, it's closely approximating one. The idea here is to bridge the gap between the diagram and the system implementers who are going to implement the system or test the system if we're purchasing an external system. Here's another look at what a primitive for this might look like. Instead of if-else logic, we use a case-based logic. So in case number 1, our inventory level is greater than our minimum order quantity, we don't have anything to do. However, if the inventory is less than the minimum order quantity, but it's not 0, we'll create a new order, and the delivery time can be tomorrow. On the other hand, if we're down to 0, we might want to create a new order with the delivery time for later today. This gives you a few examples of how you might implement a simple primitive. This is structured English. Another approach to doing this kind of thing is with something called a decision table. A decision table effectively maps inputs and outputs as best we can using a table structure like this. So on the left we have conditions, courses of action, so based on the type of the item, the time of the week, or the season of the year, and these could all be inputs into the process. We then follow a certain rule, so perishable, non-perishable, weekday, weekend, and so on, based on the set of rules that you see here. These again allow a business analyst who might not be familiar with writing computer code to describe the process in a way that closely approaches or approximates the logic that a computer might use. But yet it's still able to be read by a business analyst so that we can verify whether or not the logic is correct. Here's just an example of how you would fill out that particular decision table with additional information. A primitive, so reviewing here, a primitive is essentially the lowest level of decomposition of a process within our data flow diagram. It should be something that we can describe in less than one page, and the logic should be able to be communicated in structured English or in a decision table. When you're done doing your DFD analysis, what you'll have is essentially a set of DFDs, beginning with the context diagram and proceeding down through however many levels is appropriate given the size of the system. And then from there, you'll have a set of primitives, which are generally a document consisting of structured English instructions or decision table instructions. These are then passed on to the system implementers, who will either implement the system by perhaps doing some custom programming, or will be purchasing the system and then verifying that the purchased system adheres to the requirements you've laid out. This section we're talking about diagrams. We've talked about data flow diagrams, and soon we'll talk about entity relationship diagrams. These diagrams are turned over to a system implementation team that takes the diagrams and turns those diagrams into a working system. They do that by either building a system or purchasing a system off the shelf and configuring it. But what if the diagram itself could be somehow automatically turned into a system that does what you want it to do? What I've just described is the vision behind something called business process model and notation. We're going to introduce it to you here just to make you aware of its existence and its role in the systems development lifecycle. After this video, you'll be able to define business process model and notation, hereafter referred to as BPMN. You'll be able to describe the vision for BPMN and describe situations in which BPMN might be useful, differentiating it from other types of diagrams. The basic vision behind BPMN is that we invest a lot of time in creating diagrams. I can remember several times in my career where I've been staring at a wall that had an enormous flowchart or swim lane diagram on it. Someone had obviously invested a lot of energy and time into creating this diagram and understanding the process behind it. The trouble with traditional diagrams is we then have to hand them over to another set of humans that do the programming in the building. But what if the diagram itself could be used to effectively build the system and manage the workflow? And so that is effectively the vision behind BPMN. Let's take a little look at the details of how BPMN hopes to accomplish this. The vision behind BPMN is it's a new modeling notation that would be easily readable and understandable by everyone, so us humans, but yet semantically strong enough to let the diagrams themselves drive the execution of an information of a process. So this essentially means it has to be understandable by people like us, but at the same time be kind of strong enough that a computer can take the diagram and use it as the basis for execution. The basic process goes like this. You would build a model, and the models look not unlike flowcharts. In fact, they've borrowed much of the flowchart symbology to make it easy for people who are used to creating flowcharts and swim lane diagrams. You do this, and it's, the formal name of the diagram is a BPMN process map or process description. Then you can run the diagram itself through a process of optimization, where the computer will use a set of algorithms to essentially rearrange components and parts of the diagrams to make the process as efficient as possible. Then you can, again, part of the vision, you can press a button and something called business process execution language will come out. This is effectively computer code that will allow the computer to run the process. The idea here is that business analysts themselves might end up being both the analyst and the implementer of a system. Or in the grand vision, perhaps we can hand these tools over to the business users themselves and let them effectively design their own system that works the way that they want it to. Now, whether or not we've achieved that vision, I'm not here to argue, but that's at least the goal of what we're driving to with BPMN. The components of a BPMN will look familiar to you. So we have processes, we have decisions, we've got some sort of sequence or flow, we've got tasks that are represented here by the boxes, and then we have a start and an end. So it looks very much like a flow chart, but yet it's strong enough to be executed on a computer. BPMN, there are several purpose-built tools that allow you to draw BPMN diagrams and generate BPEL, so Business Process Execution Language. One of the most common diagram drawing tools out there is a product called Microsoft Visio. BPMN became available in Visio 2010 and has been fully available in Visio since the 2013 version. You can find it in your shapes with all of the other shapes that you might find in Microsoft Visio. This is an example of what a BPMN model might look like. So again, you're looking at something that's very similar to a flowchart in most respects, but there's a lot more data and information that's encompassed here that allows the computer to effectively execute this process. As part of your reading for this lesson, there is a link to a video that shows a BPMN simulation and process. I encourage you to take a few minutes and watch it to help you get a better idea for what BPMN is all about.